What if I told you that a new technology just got 10 billion times better? Seriously, and I'm not talking about science fiction. This is the reality of quantum teleportation. Now hold on, it's not about beaming people across the galaxy. It's about sending information in a way that could completely reshape our world. And it all starts with that absolutely mind-bending number.
10 billion times. That's the real performance leap a quantum computing company just announced. A 10 billion-fold improvement over what was already state-of-the-art. I mean, it's a number so big it's hard to even wrap your head around, and it's all happening because of a principle that honestly sounds like magic.
So you have to ask, right? How is a jump that massive even possible? It feels like it breaks all the rules of normal progress. And you know what? In a way, it does. Because the answer isn't found in our everyday world of physics, but somewhere much, much stranger.
To understand this, we have to dive into the quantum realm. The secret to all of this lies in its bizarre, counterintuitive, and incredibly powerful rules. This is where things get a little weird, but stick with me, because this is where the magic happens. Okay, so everything you're using to watch this right now runs on classical bits. Think of it like a light switch. Super simple. It's either on, which is a 1, or it's off, a 0. That's it. But a quantum bit, or a qubit, is a whole different ballgame. It can be a 1 or a 0, or, thanks to this wild property called superposition, it can be both at the exact same time. And that ability to exist in multiple states at once is the secret sauce. It's where quantum computing gets its incredible exponential power.
But superposition has a partner in weirdness, and it's called quantum entanglement. This is where two particles become linked, so deeply linked that their fates are instantly connected. Whatever happens to one particle, you immediately know what's happening with the other, no matter how far apart they are. We're talking instantly, even if they're on opposite sides of the universe.
This idea was so strange, so counterintuitive, that it famously drove Albert Einstein crazy. He called it spooky action at a distance. He just couldn't accept that this connection could happen faster than the speed of light. And yet, decade after decade of experiments have proven him wrong. It's real. It's a fundamental part of how our universe works.
Okay, so we've got these really strange quantum ideas, superposition, spooky entanglement, but how does any of that let us teleport information? What's the connection here?
Well, here's the key. We're not teleporting matter. We're not beaming atoms from one place to another. We are teleporting its exact quantum state, the pure information it holds. And the best way to think about this is like an old Enigma machine from World War II. You don't send the secret message itself, you send a scrambled mess. The important part is sending the key to unscramble it. With quantum teleportation, entanglement creates that perfect, unbreakable key between two particles.
Let's walk through it with our classic science characters, Alice and Bob. So first, Alice and Bob each take one particle from an entangled pair. These are their perfectly linked Enigma machines. Step 2. Alice has another particle, a qubit, she wants to send, and she measures it together with her entangled particle. That action, that measurement, instantly changes Bob's particle, even if he's miles away. Step 3. All Alice has to do is send Bob 2 little bits of regular data, the key, over the normal internet. Finally, Bob gets that key, makes a very specific tweak to his particle based on it, and bam! His particle instantly transforms into a perfect, identical copy of Alice's original. The information has been teleported.
Now I know what you might be thinking. This all sounds like a really cool theory, a thought experiment for a physics lab. But just recently, scientists ripped it right off the blackboard and put it into the real world.
For the very first time, a team at Northwestern University successfully teleported quantum information over a standard off-the-shelf fiber optic cable. We're talking the same kind of cable that's probably delivering this explainer to you right now. And get this, it wasn't on some clean, isolated lab setup. It was on a busy cable, already humming with regular internet traffic.
As the lead researcher, Professor Prem Kumar, said himself, this is incredibly exciting because nobody thought it was possible. I mean, proving that this delicate quantum data could survive and travel alongside all our noisy, classical data on the same network, it's a total game changer. It really opens the door to a future where the quantum and classical internets are one and the same.
But look, even with breakthroughs like this, there is one absolutely massive challenge that the entire field of quantum computing is still wrestling with.
The thing that makes qubits so powerful, their incredible sensitivity, is also their greatest weakness. They are unbelievably fragile. The
The tiniest vibration, a slight change in temperature, a stray magnetic field, any of it can corrupt the precious information they hold, creating an error. So, building a useful quantum computer isn't just about cramming in more qubits, it's about making them stable enough to actually work.
The solution has a name: quantum error correction. It's basically a whole suite of incredibly clever techniques designed to find and fix errors in qubits without actually destroying the fragile quantum state. You can think of it like a superpowered spell check for the quantum world. Mastering this is the real key. This is what will finally unlock large-scale fault-tolerant quantum computers that can solve real problems.
So why does all this matter? Why are we going through all this trouble? Well, solving these huge challenges, teleportation, error correction, it's not just some academic puzzle. It is literally about building the foundation for the next information age. A future with these fault-tolerant quantum systems, well, it looks like a quantum internet that is physically unhackable, secured by the very laws of physics. It means we get computers powerful enough to perfectly simulate molecules, letting us design new medicines and new materials from the ground up. It means unlocking solutions to enormously complex problems in finance, shipping, and logistics that today's best supercomputers couldn't solve in a billion years.
So, from Einstein's spooky action to data teleporting across the everyday internet, we are slowly but surely turning science fiction into scientific fact. And it all leaves us with one really profound question. What new things will we discover? What new realities will we create when we finally have the power to compute the impossible?